could we have a show of hands? How many people here consider themselves, let's say their professional background, their training and so on, to be on the side of astronomy, astrophysics, cosmology, that sort of thing? Okay, good show. Okay. And, are the rest of you engineers of some type? Okay, and in general physics, I'll lump you in with whichever group you want to join. Okay, thanks very much. Well, it's, as I say, it's an honor for me to be here because today, I don't know how many of you realize it, but today is the 83rd anniversary of Robert Goddard's first liquid-fueled rocket flight. He did it from a farm in Auburn, Massachusetts, my home state. The rocket was named Nell. It was 10 feet long, or high. The flight was successful. As I say, it reached a maximum velocity of 60 miles an hour. It got to a maximum altitude of 41 feet, and the flight time was 2.5 seconds. Not a very auspicious start. But when you realize that was 1926, and that we walked on the moon in 69, that's not bad. So congratulations to the Goddard family on its 83rd anniversary. The title of my little talk here this afternoon is, as you see it, I hope it doesn't lead a false impression in your mind that I have the answers to everything. Clearly that's not the case. Plasma science and engineering doesn't have the answers to everything. What I do submit is that the observations that have been made in plasma, real earthbound plasma laboratories from experiments that have been made do have a great deal to contribute to astrophysics, if the astrophysicists are willing to listen, and I hope they are. And that's one of my pleas here this afternoon. The experiments that we've done in plasma laboratories have been fairly recent, but they have been in the deep, dark past as well. And so I would claim that the first plasma scientist is Ben Franklin. He's the first guy who actually inserted a probe into a plasma. Now, the probe was a kite, and the plasma was the atmosphere in a lightning storm. But that's what he was doing. And after he survived the experiment, and we don't know how, but he did, he concluded, he was heard to remark, perhaps as he was lying on his back, I don't know, that the sky obviously was electric. Now, this was in 1750-something. And clearly his conception of what was electric was very, very primitive. The electron wasn't even going to be discovered until J.J. Thomson did it or proposed it in, what was it, 1898 or something like that. So there was a great hiatus there. What went on in that, about a 100-year period? Well, what went on after Ben Franklin was all of the experimental work that laid the foundation for electrical engineering and electrical technology. We had people like Volta, Ampere, Ohm, Weber, Gauss, and so on. But what they contributed was a bunch of diverse, disparate experiments, observations, if you will. And, you know, the three-legged stool of science, observation, theory, and experiment, testing. That was the observation, but there was no theory. Then along came James Clerk Maxwell, and it was able to put all those observations together, and with the help of a fellow whose name was Oliver Heaviside, and also with the addition of a little help from Hendrik Lorentz, he came out with 4 or 5 very compact vector calculus expressions, which pretty much tell everything that you need to know about electrical and electromagnetic theory. So there was the theory. After him, at least in the realm of plasma cosmology, came a man called Christian Birkeland. Birkeland was the first person to suggest that the causation of the aurora borealis was by particles from the sun, electric current from the sun. He was severely laughed at by people like Sidney Chapman of Chapman-Vestine theory. Perhaps you know Chapman-Ferraro cavity and that sort of thing. Chapman's idea was that the aurora was caused totally internally to the Earth by tidal fluctuations somehow in the ionosphere. There couldn't be anything coming through the pure vacuum of space because there was no charge separation in space. There couldn't be. The charges would come together and neutralize each other, or if they were like charges, they'd push against each other and diffuse. So this idea of Birkeland's was obviously lunatic. Until, of course, we launched some satellites, or really space probes, above the ionosphere and found out that indeed the power, what was causing the aurora, is a flow from the sun. How? Well, I think one of your next lectures is by Dr. Siebeck, is it? Who will be talking to you about that. In any event, moving along in the family tree of plasma cosmology or plasma science is Irving Langmuir, who won the Nobel Prize for surface chemistry in 1932. He was the first person to call a plasma. He essentially hijacked the term from biological science because he saw that plasma, our kind of electric plasma, and blood plasma had some very similar characteristics. Number one, they're both cellular. They divide into cells. Second similarity is if you put something foreign into both of those things, that invader will be immediately sheathed by some sort of stuff. In the case of blood, some of the cells in the blood will sheath the invader and try to either neutralize it or kill it. In a plasma, the invader, whatever it might be, your probe to try to find and measure voltage, for example, is immediately sheathed with what has now become called a Langmuir sheath, usually electrons. Langmuir was clever enough to come up with a device that would remove the effect of that sheath and enable us to measure voltage within a plasma, and it's called a Langmuir probe. After Langmuir came Hannes Alfvén. Alfvén was an electrical engineer, worked for the Swedish power company. They were very concerned with explosive disasters that were happening on their very, very high voltage DC transmission lines. And Alfvén found out what the problem was and was able to cure it. It was a plasma phenomenon. There was energy stored in the magnetic fields around the transmission lines, and explosive occurrences in what was called a double layer, which stopped the inductive current flow, released this energy, and so you had explosions that killed people and melted power stations and things like that. Alfvén also extrapolated those ideas into the cosmos. And he said, perhaps if there is plasma out there, the explosive things that we see, like, for example, coronal mass ejections, might be from a similar cause. Alfvén also did many things and made many contributions. I'll talk a little bit about his work in the heart of my presentation.
He stood and gave a talk just where you are some years ago in this room.
Alfvén.
Yep.
I'm on hallowed ground. Alfvén was a mentor of a friend of mine, Dr. Tony Peratt, who's at Los Alamos National Laboratory. Peratt is rather well known for his identifying, codifying, listing, and sort of getting a handle on instabilities that happen in plasma. One of the objectives in, let's say, a nuclear reaction is to try to hold the thing together for as long as you can, to maintain that plasma stable. And what happens is there are inherent instabilities in the plasma which lead to the plasma falling apart. Those are your enemies. You're trying to defeat those instabilities. Peratt has done a lot of work in that area. He also did some simulations on supercomputers. And I don't know why this thing is banging. I'm sorry if it sounds like thunder in the background, but I... Can you hear me then?
Turn it up.
Hello. Okay, now I've got this mic on. Is that?
You might want to move it up on your time.
There we go. All right. Okay. And in my introduction, I was introduced as being a professional TV person, right? Sorry about that. And anyway, Peratt did these simulations of plasma and actually was able to create something that looks like a spiral galaxy in a computer simulation in a supercomputer. And you say, well, so what? Well, there was also at Los Alamos a fellow named Winston Bostic who was able to create in actuality in the laboratory a plasma structure that looked exactly like a barred spiral galaxy. And you may also say, well, so what to that too? Just because he was able to do it doesn't mean that barred spiral galaxies are made this way. True. One other thing that's kind of interesting is that the velocity profiles of those galaxies, which drive astronomers through the roof, was the motivation for dark matter back in the 30s. Charlie Alcock's Machos, Marty Milgram's MOND, modifying Newton's dynamics, were all caused by this anomalous velocity profile. The profiles that Peratt's simulations predicted and the profiles that Bostic's models produced are exactly what we see in the sky. And we don't need any of this fairy dust to produce it. Here's Christian Berkman in all his glory, in his experimenter's hat and his Chirella. He actually made a model in the laboratory of what he was proposing. There was a magnetic field, an electromagnet inside that ball to produce something that was akin to the Earth's magnetic field as best he knew it. He went out and created a string of observatories on the north slope of Norway, directly below the aurora, and was actually the first person to measure what we now call substorms. He measured the magnetic fluctuation and recorded it, and that's the title of his book, The Norwegian Aurora Polaris Expedition, and published in 1908. Yeah, he also discovered that electrical current often travels in twisting pairs in a plasma, and they're now called Birkeland currents. This is a little picture that I got off the web, and it was published by you folks here at Goddard, by Jonathan Eastwood. I don't know if any of you know him or know where he worked. I think he's also at Berkeley. And I was extremely happy to see the words ampere and volt in there. Most times you see any explanation about things in space written by astronomers, you never see amp or volt. You never see anything other than, oh, there was a magnetic field and it moved and this is what happened. And then the question of why did it move? Did it take it into its head to move? So I applaud you're doing that. I have some quibbles with some of the phraseology. I don't like the flux rope business, but it's all right. I think that's a step in the right direction, and I applaud Dr. Eastwood. I presume he's a doctor. He should be. Here is a little diagram of a Birkeland current, and you can see it turns out to be a pair of helix currents. The yellow streak there is supposed to show you there's some plasma, i.e. a conducting path. There's also, you can see the magnetic lines are drawn there. I have some quibble with magnetic lines. There's no such thing, and if you think about it, you realize what I'm saying is correct. There is no such thing in three-dimensional reality as a magnetic line. It's a draftsman's artifice to show you where the field goes. A magnetic field is a vector field. It's a continuum. It's a fog. It's an uncountable number of points in a set. Each point has a direction and a magnitude. That's all there is. There are no pinstripes in a magnetic field. But in any event, it's a nice thing to think about, because you can think about electrons going around these magnetic fields. They don't. They go in a circle in a magnetic field. It's because of the Lorentz V crossed, the cross product of the velocity into the magnetic field gives you the force on the particle. So if a positive charge is transverse to the magnetic field, it won't go through the magnetic field, it'll be constrained to go in a circle. If the current or stream of charges is parallel to the field, it won't be affected. And the particle, the cross product of two things that are parallel is zero. So there's no force on a field-aligned current. So the superimposition of the circular component with the linear component for an arbitrary angle of input of current is, of course, circle plus straight line as a helix. Now, why they form in pairs is not an easy question. They do, and that's a laboratory finding. The little curve on the right just shows that if these things get too far apart, there seems to be a force that pulls them back together. If they get too close together, there's a force that pushes them apart. So you see them very often in parallel pairs like this. Here is an example, I think, of a classic example of Birkeland current. If you can see, I don't know how good your eyes are, or how good the slide is, but can you see the two parallel? Do you see the twists? This came from Göran Schammer's Solar Physics Institute in Sweden. And when they saw this, they described it as two parallel snakes with a stripe down their back, and they're twisting. I submit in this day and age they should know how to recognize a Birkeland current. But the properties are all there. So this is, I won't talk too much technically about it, but for those electrical engineers in the group, you recognize the voltampere characteristic of a Crookes tube discharge. This is essentially describes plasma. You can see that it's clearly a highly nonlinear, it's a laughably nonlinear kind of stuff. A resistor would plot out on this plot as a straight line. So clearly there are three operating modes for plasma, the so-called dark mode on the left, the glow mode in the middle, and the arc mode over here. And there seems to be abrupt transitions between those modes. If you have a plasma and make it operate in the range B to C, that's where Geiger counters operate. That's the so-called current saturation region. Because clearly, excuse me, you can change the voltage or the E field inside the plasma quite a bit and not get much change in current. But if you get an alpha particle that comes screaming through the plasma, it'll ionize one of the atoms and click, you'll get a click or a buzz or whatever. Up at the top is the so-called Townsend discharge. This is the region where it used to be called, what is it, St. Elmo's fire on the top of a wooden mast of a ship. The example of plasma in the dark mode is our ionosphere, as long as there's no aurora in there. But obviously, how do you know it's there? Well, you can bounce radio waves off it. If you're a ham radio operator like I am, you can, if things are right and the sun is doing the right thing, which it isn't now, you can get F2 refraction from the ionosphere and talk to Australia. So you know that there's dark mode plasma there, but that's the only way we can tell. The glow mode, that's easy. That's an example of that would be the neon sign. You know, eat at Joe's. That's a glow mode plasma. So I maintain is the corona of the sun. Arc mode plasma, that's also easy. That's the electric arc welding machine. It's also lightning. It's also the spark that you see when you scuff your feet across the rug in a winter night and reach out and touch the doorknob. That's plasma in the arc mode. A couple of things that are not too obvious, though, but I would like to point them out, and that is that at no point, except for the origin, which is not really very interesting because it says there's no voltage and no current, so there's nothing going on in the plasma. You're lucky to have a plasma at all. But at all the other points in that characteristic, there is no point that does not have a finite, non-zero electric field. And so don't let me hear anybody ever say that the electric field must be zero in a plasma. There's laboratory evidence that says that isn't true. As a result, for those of you who, we'll talk a little bit about this in a minute, but for those of you who know Maxwell's equations, the curl of E equals the is proportional to the time derivative of the flux density. That's the excuse why people say magnetic fields are frozen into plasmas, because if the electric field is zero, then the curl of zero is zero. And so if zero equals the time derivative of something, it means that something ain't moving. So the magnetic field has to be frozen. Well, that puts the error to that argument. There is no place where the electric field is zero. Another thing you might notice is that, for example, in a couple of ranges, F to G and I to J, the slope of the curve is negative. The slope of that curve is the dynamic resistance of that stuff. And what you're really saying is, if you're in a point in the plasma operating at, say, point F, and you've got this bunch of ions and electrons dancing around each other, the E field on those particles is the force per unit charge on each of those particles. And clearly, a population of things will move to reduce the force on them. In other words, if you push on me, I'm going to move back. And electrons are the same way, and so are positive ions. So the plasma has a tendency to move from point F to point G. It wants to reduce the force on each of me. Well, how does it do that? Well, it's got to raise the current density. What's current density? Density. Current density is how many amperes per square unit of area do you have? So what does the plasma do? It decides voluntarily, if you will, not to use the entire cross-section of the plasma, but to use a lower cross-section. So it increases the current density by reducing the area that it uses. In other words, it forms filaments. So a natural tendency of plasma is to become filamentary, at least in the low current density range of the normal glow mode and in all of the arc mode. So people talk about sheet lightning, but I have a sneaking suspicion that that's a certain form of glow discharge, not arc discharge. Most lightning strokes are filaments, jagged three-dimensional filament, very narrow. Okay, enough of the physics. Oh, just some plasma properties. I hope to go through this relatively quickly because I've got more interesting things and I don't want to overstate my time. I think we've talked about most of those things, if not. Oh, by the way, electrostatic analyses usually fail. Most people look at some of the things that plasma physicists do and they say, oh, that can't happen because if you use the equation Q1, Q2 over R squared, they'll go together, they'll separate. Plasma forms cells and insulates regions of plasma from nearby regions of plasma, just like blood does. So simple electrostatic analyses usually fail when they try to use it. You've all probably heard this one. Here's a pair of copper balls, like little billiard balls, more like shotgun pellets of copper. If you remove one valence electron from both of those spheres, you will levitate the top against the entire pull of the planet Earth to pull it down. One electron out of the some almost 6 trillion that are in there available will levitate that copper ball. On the other hand, if you take the electron from the top one and place it on the bottom one, then you'll have ohm-like charges and they'll slap together with twice the weight of the original one. So this is a slide that people in my side of the fence use to show that electric force is much, much more powerful than gravity. But then the argument is turned right around and used against this by people who say, well, yeah, so therefore if it's that strong, you can't have charge separation in space. Pluses and minuses will come together. Well, that isn't necessarily true because we do have plasma in space. But this was the primary criticism, as I referred to before, against Birkeland's idea that stuff was coming from the sun. There is a sort of a dichotomy between the theoreticians who claim to be plasma scientists but who never want to get near a laboratory, and the experimentalists, the experimental guys who are in the laboratory. Most of the assumptions that are made, because you want to use magnetohydrodynamics, is you use a homogeneous model. Well, it turns out that plasma is almost never homogeneous. The conductivity is infinite. No, it's not. It's not infinite. You saw that volt-ampere characteristic. There's a finite non-zero resistance to every point in the plasma. The E field along B is zero. No, it's not necessarily. The conductivity of a material is due to a couple of things. One is, the mobility of the charge carriers is one thing, which is very high in a plasma, but the density of those charges is another one. And in a cosmic plasma, the density ain't that great. You know, so many per cubic meter. So the conductivity is not necessarily infinite, and the E field is often not zero. The Prozanian idea is wrong. I'll talk about that in a minute. And these ideas of a double layer, I haven't really mentioned what a double layer is, but a double layer is a wall that separates two cells of plasma, much like the cellular wall would separate blood cells. And if you ignore Perat's instabilities, you're going to get the wrong answer. And there's several other things. The first one is one of the things that sort of I worry about all the time, and that is that you only write magnetic field line pictures and never worry about the currents that actually create those magnetic fields. I claim that you will make progress if you think about the currents as well as the fields that they produce. And this last one, of course, is the magnetic reconnection idea, which I'll hopefully get to. This is, just briefly, what is a double layer? If you have 2 points, let's say A and B in a plasma, and they're at radically different voltages, the plasma doesn't like that. But the plasma generally cannot vary the voltage linearly between point A and point B. What you'll see if you use your Langmuir probe is you go from point A, and if point B is at a lower voltage, you'll get lower and slightly lower as you get away from A. And all of a sudden, whoop, the thing will drop almost to the voltage of B, and then it'll stay pretty much at the voltage of B. In other words, the transition in voltage happens in a very narrow range of distance. That's a double layer. And what you see here is a sort of a stylized one-dimensional double layer. Clearly, the top one is there's a voltage of, let's say, point A, which is high, and a voltage at point B, which is low. And so that obviously, by definition, the electric field is what? The negative of the gradient of the voltage of the scalar field, right? So if you plot the slope of this upper curve and then turn it upside down, that's how you get this. So clearly, that's why charged particles are accelerated in a double layer. It's like a pebble on a slippery hill. You slide down that hill. The force on the positive charge that's doing the sliding is maximum right in the middle. So the E field is highest, the force per unit charge to push it to the right. That's just by definition. But now what about this bottom layer? Well, another one of Maxwell's equations is that the divergence of E is proportional to the divergence of epsilon E, the permittivity times the E, is equal to the charge density. The divergence relationship in a one-dimensional deal like this, it just turns out to be the simple derivative with respect to distance. So if you take the derivative of this curve, i.e. plot the slope of this curve, you get this curve. You can see that the slope in here is a maximum right there. The slope at the top is flat, so it's zero, so the slope is okay? So what this means, in order to get that voltage picture, which gives you, of course, by definition, that force picture, requires a double layer of charge. Now, what keeps the double layers from slamming together? That's like a capacitor with plus and minus charges. Why doesn't it just slam together? And the answer is that's the reason Irving Langmuir got the Nobel Prize. He figured out why that doesn't happen. It doesn't happen because it's a dynamic kind of a thing, not an electrostatic kind of a thing. And it requires a certain number of plus charges going one way and a certain number of electrons going the other. And this can become extremely stable. It also can very abruptly become unstable and disappear. In which case, it's just like opening the switch in a transmission line. That if the double layer, which is conducting current, disappears, explodes, that's what Alfvén saw in those power lines in Sweden, you'll get a disruption in the current. These, we believe that these double layers happen all over the place and can have tremendous voltages. Of course, the galactic business is all supposition, speculative. So is the solar one. But it appears that there may well indeed be a double layer associated with the surface of the sun that occurs somewhere in the neighborhood of the chromosphere, above the photosphere, which would be responsible for accelerating positive ions down that potential hill outward. It also has the potential to use a pun, to explain the solar temperature minimum. The idea of a smooth laminar flow of ions and then sort of white water at the bottom. So I don't want to get into that because that's all speculative, and I'd like to stay with what we really know. So there's my hero, Hannes Alfvén. He did so many things that it would take me all day to tell you how many things he did. He's obviously the father of plasma cosmology. He, in 1940-something, 41, suggested that there could be longitudinal waves in plasma, as well as the transverse electromagnetic ones. And he was laughed at. Oh, that's impossible. No, it can't be. And so one day, and I think it was 1942, at a convention, a meeting, scientific meeting in Chicago, he was expounding on these so-called waves in plasma. And it happened that Enrico Fermi was in the audience. And so Alfvén's babbling along about how great these things are and what he can do with them and so on. And all of a sudden, Fermi begins to nod. And the story goes, Fermi was heard to whisper, "Yes, this can happen. Yes." And all of a sudden, all the audience is going. And so Alfvén waves were accepted. They were also actually verified in the laboratory, about a year later, something like that. I talked about the explosive release of energy. He's also credited for the idea of CIV, which is the critical ionization velocity. The question, how do you get charge separation in space? Answer, you have a plasma and you have a neutral gas cloud approaching each other with relative high mutual velocity, relative velocity. If the kinetic energy of the neutral particles, 1/2 mv squared, is higher than the ionization potential, the neutral gas becomes ionized. It's been verified over and over and over. He was also a bear about this idea of magnetic fields not being frozen into plasma. And the reason he was is because he was the guy who came up with the idea in the first place. He knew Maxwell's equations. And it was only that he came of late to the idea that there had to be some little tiny electric field, and therefore magnetic fields are not frozen in plasma. It's a good thing they're not, too, because the only way you generate current is by relative motion between a conductor and a magnetic field. That's what keeps the lights on in this room. And the plasma is the conductor part of that little operation. So if plasma is moving with respect to the magnetic field, you will generate a current in the plasma. And therefore, the current will generate the magnetic field. That's how the magnetic field gets there. He also said there's no such thing as magnetic reconnection. We'll talk a little bit more about that in a bit. And also the idea that there's no such thing as an open magnetic field line. You hear helioseismologists talk about the footprint on the sun from which the magnetic lines of force emanate, and then they go out to infinity like the skirt of a ballerina and all that. There's no such thing as an open magnetic field line, and I'll try to show why. There's a typical sketch of a magnetic field. as shown in every physics textbook in the world. You put current in the direction of I there, put your thumb in the direction of the current, and your fingers will show you the direction of the flux. Also works if you put your fingers in the direction of the current, your thumb will be in the direction of the flux, so it works both ways. But the point is the magnetic field lines are a draftsman's artifice to show you where the magnetic field is strong. At the top, which is where the field lines leave, is the North Pole, and the magnetic field lines are very dense there, so it's a strong place. By the way, the arrows are a little bit misleading. There's nothing moving. These are not flow lines. These are simply lines that show you the vector direction of the point in the field at that point. So there's nothing moving around those lines. Also, you may think, well, look, there's open field lines at the top and open field lines at the bottom. Yeah, sure, because we don't have a big enough piece of paper. You can draw open contour lines on a map of a mountain, and if your map isn't big enough, you will see 1,000 feet goes off here, and it's off, and then 1,000 feet comes back here on the bottom. It's exactly the same as we're seeing here. Actually, this is, if I can get it to show. Yeah, this is more like what a magnetic field might look like. Even that's not right, because there's no discrete quantized steps. It's a smooth continuum. But wouldn't you rather draw the one on the left? It's a hell of a lot easier than drawing the one on the right. But don't let that artifice make you, there's a word that I love. It's called reify. Don't let a concept become a real three-dimensional object. Pinocchio is a wooden puppet. He's not a boy who can do things. So is a magnetic field line, just an abstract concept. This is a model for the double radio source galaxy that Alfvén came up with. It's, I don't know if you can see it, it's supposed to be Cygnus A. The blobs on the left are what we sort of see about Cygnus A. The galaxy itself is this little thing in the middle. And these are the radio emission patterns seen by the Very Large Array in Socorro, New Mexico. Alfvén said that, by the way, I should have said this when we were talking about double layers. If you think about that big drop in voltage and the current that's going through there, the product of volts times amps is watts. So a double layer is where most power is released. And it's released in a plasma as radio noise. So a double layer is almost always noisy. You can hear it by its radio transmissions. And you can see that if indeed this model is correct, it shows current paths, which are sort of like two cups. It's kind of like an hourglass kind of thing. There's what the picture really looks like. And of course, there's also that jet, that highly collimated jet that goes out from the central galaxy in both directions, stronger to the right in this picture. And so the astronomers go through all sorts of tortuous logic, Schwarzschild event horizons, and various types of black holes, and all sorts of things. I mean, they have a problem. They work with one force, and it only attracts. So how are you going to get things to squirt out energy like that? That's not like a garden hose. A hydraulic jet will dissipate. That's highly collimated over a distance of light years. Well, it turns out that in the laboratory, there's a thing called a plasma focus device, and it's a piece of cake to make a beam like that. And in fact, if we were to remove the back end of this thing and be able to somehow support the middle of it against gravity from falling apart, this back plate, unfortunately, is the only thing that holds the middle part there. But if you could remove that back plate, you'd get a double beam just like the one you see over there. Occam's razor says if there's a simple answer, at least consider it. And this is relatively simple. There's the artist's conception of what that thing looks like. That hourglass figure, here's an example of it. You can almost see the polar double layers along this polar axis. There's There's a phenomenon also, I didn't mention it in regard to the Birkeland currents, called the Z-pinch, which is when this thing, at places the two Birkeland currents can come together, form a very high intensity release of energy. And there's also a process called Markland convection, which happens at the Z-pinch, which accretes material. It accretes it much more efficiently than any accretion disk that astronomers seem to be able to come up with. My friend Tony Peratt says that he knows many astronomers at Los Alamos who've tried to come up with accretion disk models on the supercomputers there, and they do so only by adding plasma to them. Don't take it from me. That's what Tony Peratt tells me. But anyway, the Markland convection is a good way to do that. Here's over time, a picture of that nebula. And you can see that from 1989 through 2007, the number of double layers, if that's what indeed they are, here they're very easily, you can see there's 3 pairs of them here, very strong one at the top. So it changes over time. I'm sure astronomers will tell you, no, it's not double layers, it's shock waves. Well, okay. Here again is again that hourglass look, and if you use as an amateur astronomer, I use the phrase "use averted vision" if your eyes aren't good enough. You can also use averted imagination. I don't know. Well, maybe you have to use imagination here, but do you see some double layers, or maybe you want to call them shock waves? But there they are anyway. And this same sort of hourglass shape. And it goes on and on and on. There are many, many objects like that. This is the red square one. And you say, well, that doesn't show like an hourglass. Yes, it does. See the curvature here, and the curvature here, the curvature here, and the curvature there. I have some astronomer friends who said, look, Don, just because something looks the same doesn't mean it has the same causality. And that's right. That's absolutely right. But there's also another old phrase that says, if it walks like a duck and quacks like a duck, well. Here's Tony Peratt's simulations. This is a cross-section of a Birkeland current. Whoop, I'm sorry. Here, and that's how he started the simulation. He put in the simulation, he put Maxwell's equations. He also put Newton's law of gravity and let the thing go on in time. And eventually it ended up showing what looks like I think that's M81. I don't know. I don't know. Looks like a galaxy. Again, just because it looks like it, does it? No. But it's nice that this happens to have the same velocity profile, radial profile that does, without any dark matter or any other fairy dust. Winston Bostick at Los Alamos actually took 2 plasma focus devices and aimed them at each other like a pair of guys with dueling pistols, and actually created that rotating galaxy in the laboratory out of plasma, real plasma. Oh, his last quote. I have a copy of his paper, which I gave to Jan. And the last line in the paper is what you read at the bottom. So we don't expect these ideas to be instantly accepted. What we would like is to not reject them out of hand and just give them a look. And don't say you have if you haven't. Just give them an honest look. This is straight out of here. Goddard produced this picture of galaxies on a string. I don't want to get into the Big Bang business, but there's some questions about whether these structures are too big to be to accrete in the length of time that the Big Bang says the universe has been around. But I will submit that the formation of galaxies along intergalactic Birkeland filaments is consistent with Alfvén's model, Peratt's simulations, Bostick's lab experiments, Markland convection, and Z-pinches. So take it as you will. Oh, I don't know whether we have time to get into this pulsar business, but are they really rotating stars, or are they reflected waves riding on a plasma transmission line? We've all experienced the Northeast blackout. I'm old enough to experience both of them. And they were caused by pulses riding back and forth along a transmission line. And it's the easiest thing in the world in an electrical engineering laboratory to create a relaxation oscillator that puts out pulses, a kilohertz pulse. 1,100 times per second, it's 1 kilohertz. It's easy. It's a sophomore level lab experiment. The days when I was in school, we actually had a transmission line and we could measure those pulses and watch them go back and forth, and it was great fun. If you want to believe that you've got something the size 20 miles wide and the mass of the sun rotating about 1.5 times the speed of a dentist drill, you're free to do it. For me, it's beyond the believability curve. But especially when electrical processes can produce it so easily. I really highly recommend that paper. That is a paper written by Healy and Peratt in 1995. It explains 17, it replicates, they did an experiment in the laboratory with a transmission line, ran pulses back and forth, and replicated 17 of the known properties of pulsars. The frequencies are just as stable. Anyway, and this idea of a neutron star, I know that some astronomers have given up on the neutronium business and want to talk about strange matter. Am I right on that? I think. Because they realize that there's some problems with the neutron. A lone neutron will decay in 14 minutes. And you say, well, that's all right because the pressure holds it all together. It seems to me you have to answer, you've got to go one or two ways. Either the neutron star sprung into existence at the instant of the Big Bang, which of course is not really possible, or it accreted. If it accreted, what kept the first 6 neutrons together until you get the 9th and 12th on there? So also there's this idea from nuclear chemistry of the isle of stability. If you plot the number of neutrons on the vertical axis and the number of protons on the horizontal axis of all the known elements, including the man-made ones, they cluster right together on that white curve. A neutron star is made up of neutrons only. That's a point on this vertical axis way up there somewhere. And it's well known that any isotope that's too far away from the green and the yellow will radioactively decay and go toward the white. So it seems to me that the idea of a neutron star has a lot of, as Lucy's husband says, a lot of splaining to do. Oh, these are just some facts that you can either agree with or not agree with, but I hope I've at least set the groundwork for them being the case. In the negative, magnetic fields are not frozen into plasmas, and I hope I've told you or given you some reason as to why that's true. Magnetic fields follow a closed path. They don't have any beginning or end. You can say, well, yes, you can have a curl-free magnetic field if there's no curl, if it's a straight, and that's the kind of magnetic field that's produced by a bar magnet. That's fine, but we haven't found any bar magnets out in space. So all of the magnetic fields we see have curl. And if they have curl, they're caused by a current density, Maxwell. I talked about the magnetic field lines. We're nose to nose with this problem. Let me just sort of tell you what I think, and you can argue with me afterward if you like. The idea of classic magnetic reconnection is that 2 magnetic field lines, like number 1 and number 2, approach each other. Why? Don't ask. They approach each other. If they approach each other and then they come together and they kiss at the center of that X, and then they break apart in the vertical direction and become 3 and 4. And, quote, because plasma is frozen into magnetic fields, onto magnetic field lines, as the lines, so the story goes, move from point 2 to the middle to 3, the plasma, according to the dashed line, is dragged along with it and thrown out into space. That's the basic idea of magnetic reconnection. Now, it's more complicated than that, but that's mainly it. I maintain there are 2 errors there. There ain't no such thing as a magnetic line of force in the first place. It certainly isn't an extant, real being in the cosmos that can do anything or push on anything. And B, even if you forget about the magnetic lines and talk about magnetic fields, plasma is not frozen into a magnetic field. So this doesn't work. And by the way, the only way you can get that sort of picture, this is one way to get it. Not the only way, but one way to get it. If you have 2 parallel currents given by the X's or the tail feathers of the arrow, there's 2 currents going into the board. The right-hand rule says there's a B field around each of these. And the center there of the little square box is essentially this picture here. Can you see it? On the right, the flux is up. On the left, the flux is down. The central point, this point right here, the point in the exact center of that box, if you stop to think about it, the current on the right produces a flux upward, vertically upward. The current on the left produces a flux, actually a flux intensity, H for the electrical engineers, downward. And obviously they're equal if the currents are equal. And these two cancel each other out. That's the reason that's called a null point. The magnetic field strength there is 0. Well, it turns out that the energy stored in the magnetic field is proportional to the square of the magnetic field strength, B squared. And a place like this that you can identify where B is 0 means there ain't no energy stored there. So how can you release energy from a point that doesn't store any energy? You can't. What you can do, and there's a tremendous amount of energy perhaps stored in this entire magnetic structure around these two currents, is you can shut off the two currents or just shut off one of them. All of a sudden the field collapses, and where does the energy go? Explosively radiates and brings along parts of the wire, and in cosmos the wire is plasma. So it drags the plasma and expels it. It's a possible explanation. It's Alvian's explanation for the CMEs. Here's this is this business, I don't think we have time to go into it, of whether the Earth's magnetic field is open or closed. I think you guys, just recently there was some question about that. If the interplanetary magnetic, the IMF, interplanetary magnetic flux is flowing from south to north, as it is in this case, the red dots are neutral points. But you notice that no member of the interplanetary magnetic field gets to go through the Earth. It's locked out by that configuration. In the case when the IMF is flowing from north to south, then the cusps are open and anything can get into the Earth. But as I understand it, it was within the last month or so, astronomers had discovered that even though this was what was going on, they discovered that something was getting through, and there's a big question now as to how that happened. And if the magnetic field is closed, how did this stuff get in here? And I don't know, but that's an interesting topic. My point is that if you're going to try to plot these lines of flux, go ahead and do it. But please remember that the lines aren't really there. They're in here. They're on the blackboard, but they're not in space. They don't really do anything. They can't, any more than Pinocchio can do anything, can cook your dinner for you. They can't. They're not real. Okay, just as to end up here, there are some cautions that I'd like to leave with you. One is electrical activity and its effects in space should not be ignored. I don't say they're all correct. I don't say they have the answer to everything. Of course not. But please just don't cast them off and say something like, oh, we've considered it, but it doesn't work. Oh, there can't be any charge separation in space. Don't say anything like that. Take a look and see what you think. The idea of new properties and mechanisms, open-ended magnetic fields, there ain't no such animal. That sort of thing. New science should not be invented until you take a look at all the old science. And I submit to you that people like Maxwell, Langmuir, Birkeland, and especially Albion have a lot to contribute to astrophysics. The last slide I have is to show you something that I picked up, and you can do it too. I think it's still there on the web, of an example of, I think, how if you don't understand the things that, not I, but Hannes Alfvén and Irving Langmuir have been saying for centuries, or at least for decades, you're going to get in trouble. Read this. In plasma physics, it is well known that magnetic field lines are frozen into an infinitely conductive plasma. Wrong. That's error number one. They're not. 2, since charged plasma particles are confined to circular orbits around magnetic field lines, well, all right, I'll let that one go because they are confined to circular orbits within a magnetic field, even though the lines don't really exist. That's not a bad error. This means that infinitely conductive plasma is wrong. There's no such thing as an infinitely conductive plasma. There's not a superconductor out there. They're good, but they're not superconductors. Will not diffuse across field lines and mix. Okay. Second paragraph.
Conversely, two distinct field lines will remain separate since they cannot penetrate the intervening plasma. Okay, two distinct field lines will remain separate. Then how in magnetic reconnection can they come together and kiss? Now, the third paragraph, that's my punchline. I didn't want to show you that. In most cases, solar and magnetospheric plasmas can be described very accurately with such a theory. Really? Then how come tokamak hasn't worked in the last 60 years? Do they really know what's going on? Straightforward application of the theory would remove the possibility of ejected solar plasma penetrating the magnetosphere, since the plasmas would not be allowed to mix. Nevertheless, based on observation and known technological disruptions, we know that they mix. And then it ends in a whimper. But how? Okay, do you know what? Did you see what the bottom line was? Do you know what august institution came out with that? Don't worry, it wasn't here. It's the Princeton Plasma Physics Laboratory. If you look up, the tokamak boys, right? If you look that up, hit that on the web, and then click on where it says physics, you will see that. And without being too strong, I really think they should get it off of there. Anyway, I would just like to leave you with a quote from Hannes Alfvén that really expresses everything that I wanted to say here today. And Alfvén said, when running a lab, I found that one of my most important activities was to go from room to room and discuss in depth the problems that a certain scientist or group of scientists was trying to understand. It often happened that one group reported that in their field, they had a special problem which they could not possibly understand. I told them that if they cared to open the door to the next room, it was not locked. Just this special problem had been solved half a year ago, and that if they injected the solution into their own field, it would take a great leap forward. Often they were not at all happy for this suggestion. That's the main barrier to scientific advance, in my estimation. So what I urge everyone, I'm talking about myself, but people in my own field as well, knock on the door. Thanks very much.
A very auspicious start. But when you realize that was 1926, and that we walked on the moon in '69, that's not bad. So congratulations to the Goddard family on its 83rd anniversary. The title of my little talk here this afternoon is, as you see it, I hope it doesn't lead a false impression in your mind that I have the answers to everything. Clearly, that's not the case. Plasma science and engineering doesn't have the answers to everything. What I do submit is that the observations that have been made in plasma, real earthbound plasma laboratories from experiments that have been made do have a great deal to contribute to astrophysics, if the astrophysicists are willing to listen, and I hope they are. And that's one of my pleas here this afternoon. The experiments that we've done in plasma laboratories have been fairly recent, but they have been in the deep, dark past as well. And so I would claim that the first plasma scientist is Ben Franklin. He's the first guy who actually inserted a probe into a plasma. Now, the probe was a kite, and the plasma was the atmosphere in a lightning storm. But that's what he was doing. And after he survived the experiment, and we don't know how, but he did, he concluded, he was heard to remark, perhaps as he was lying on his back, I don't know, that the sky obviously was electric. Now, this was in 1750-something. And clearly his conception of what was electric was very, very primitive. The electron wasn't even going to be discovered until J.J. Thomson did it or proposed it in, what was it, 1898 or something like that. So there was a great hiatus there. What went on in that, about 100-year period? Well, what went on after Ben Franklin was all of the experimental work that laid the foundation for electrical engineering and electrical technology. We had people like Volta, Ampere, Ohm, Weber, Gauss, and so on. But what they contributed was a bunch of diverse, disparate experiments, observations, if you will. And you know, the three-legged stool of science: observation, theory, and experiment, testing. That was the observation, but there was no theory. Then along came James Clerk Maxwell, and it was able to put all those observations together, and with the help of a fellow whose name was Oliver Heaviside, and also with the addition of a little help from Hendrik Lorentz, he came out with 4 or 5 very compact vector calculus expressions, which pretty much tell everything that you need to know about electrical and electromagnetic theory. So there was the theory. After him, at least in the realm of plasma cosmology, came a man called Christian Birkeland. Birkeland was the first person to suggest that the causation of the aurora borealis was by particles from the sun, electric current from the sun. He was severely laughed at by people like Sidney Chapman of Chapman-Vestine theory. Members, you know Ferraro cavity and that sort of thing. Chapman's idea was that the aurora was caused totally internally to the Earth by tidal fluctuations somehow in the ionosphere. There couldn't be anything coming through the pure vacuum of space, because there was no charge separation in space. There couldn't be. The charges would come together and neutralize each other, or if they were like charges, they'd push against each other and diffuse. So this idea of Birkeland's was obviously lunatic. Until, of course, we launched some satellites, or really space probes, above the ionosphere and found out that indeed the power, what was causing the aurora, is a flow from the sun. How? Well, I think one of your next lectures is by Dr. Siebeck, is it? Who will be talking to you about that. In any event, moving along in the family tree of plasma cosmology or plasma science is Irving Langmuir, who won the Nobel Prize for surface chemistry in 1932. He was the first person to call a plasma. He essentially hijacked the term from biological science because he saw that plasma, our kind of electron, could we have a show of hands? How many people here consider themselves, let's say their professional background, their training and so on, to be on the side of astronomy, astrophysics, cosmology, that sort of thing? Okay, good show. Okay. And, are the rest of you engineers of some type? Okay. And in general physics, I'll lump you in with whichever group you want to join. Okay, thanks very much. Well, it's, as I say, it's an honor for me to be here because today, I don't know how many of you realize it, but today is the 83rd anniversary of Robert Goddard's first liquid-fueled rocket flight. He did it from a farm in Auburn, Massachusetts, my home state. The rocket was named Nell. It was 10 feet long, or high. The flight was successful. As I say, it reached a maximum velocity of 60 miles an hour. It got to a maximum altitude of 41 feet, and the flight time was 2.5 seconds. Nitric plasma and blood plasma had some very similar characteristics. Number one, they're both cellular. They divide into cells. Second similarity is if you put something foreign into both of those things, that invader will be immediately sheathed by some sort of stuff. In the case of blood, some of the cells in the blood will sheath the invader and try to either neutralize it or kill it. In a plasma, the invader, whatever it might be, your probe to try to find and measure voltage, for example, is immediately sheathed with what has now become called a Langmuir sheath, usually electrons. Langmuir was clever enough to come up with a device that would remove the effect of that sheath and enable us to measure voltage within a plasma, and it's called a Langmuir probe. After Langmuir came Hannes Alfvén. Alfvén was an electrical engineer, worked for the Swedish power company. They were very concerned with explosive disasters that were happening on their very, very high voltage DC transmission lines. And Alfvén found out what the problem was and was able to cure it. It was a plasma phenomenon. There was energy stored in the magnetic fields around the transmission lines, and explosive occurrences in what was called a double layer, which stopped the inductive current flow, released this energy